Welcome to our session. First of all, I would like to thank Mustafa Teseven, who deeply contributed for this conference, and all of the representatives of the energy sector. I hope we can do this sort of conferences on an international level, and I hope we can discuss the issues evolving in this area. The fact that this session's name has technology in it will make it even more interesting, because we know how to make use of technology. We can see it on our streets too, but when it comes to wind, we only think of the pinwheels and windmills. In the last 7 or 6 years, we have started to see investments on wind, and the perception is about to change. I mean, when kids are asked to draw pictures about energy, they draw wind turbines. Even one turbine can support thousands of residents. When I say this sentence, people are amazed. This is not a previous event. I mean, this is a current one. But only when we look at it, we think of these. When we take a closer look, how this holds the R&D process, the efforts, and thousands of hours of work. Electricity it produces, nearly zero emission, are just a few benefits. Nikola Tesla had an article at 1931, and its article was named Our Future Motive Power. He said he couldn't understand the wind, but it was supposed to be used as a power. Previously, it wasn't even considered as a source of electricity or power, but nowadays we think very different. Thank you so much, everyone who supported. So now I will want to give the floor. But well, before giving the floor, we talked about the turbines. Even though they are in smaller megawatts, they were homemade products, and I was so proud. I hope this will encourage our local investors too, and I hope that one day we can discuss our homemade products too. I also want to thank everyone who attended this panel, and now I would like to give the floor to Mahir Tosun, who is the sales manager of Siemens Sanayi. Hello, first of all, welcome. Here, especially in TWEC, in such a conference, seeing so many technical personalities here really makes us feel happy. I would like to talk about the innovations on the direct drive technology, but I don't want to go on too much technical details, but I want to talk it on the aspect of the investors and its effects. Well, Siemens has a direct drive technology, and there are 4 main benefits, and these are the ones I want to emphasize. First one is the permanent magnet. As a result of the permanent magnet, we can have a new and high performance drivetrain. This can give us better performance. The second one is that we have a simple design with less moving parts, and as a result we have easier maintenance. The third one is the fact that it's a compact and a lightweight design, and this is a major advantage for transportation and installation. So as a result, our 4 main points, which is one of the most important one, this can hold more lift, and as a result, we can have wider blade scales, so we can have better performance. So my first point is the direct drive technology of Siemens, and I will talk about it a bit first. Direct drive technology of Siemens has permanent magnets, and these permanent magnets, well, we will discuss this, but I will give you a small example. 10 millimeters of permanent magnets is equal to a 10 centimeter of copper winding. So we have smaller scales, and we need less, as a result, we need less moving parts. So with direct parts, you know, we have 50% less components, and it still works. So we decided to go on with it, and what's left behind has proven itself, and we moved on with components such as blades and hubs and towers. Yes, we got rid of 50% of the hub, but we had a passive cooling system in a reliable top mounted, and we isolated this. So as a result, well, we have to stop at one point. The Siemens turbines are always compatible to use in offshore. We always make sure that our equipment can function in offshore. So another point of Siemens direct drive is an accumulation of 20 years of lifetime stress. I mean, to talk about this feature, well, this may seem new to you, but this is not new for us, for engineers. We had accelerated life tests, so we tested our equipment that, or about whatever it may go through for 20 years. So we checked the performance of the generator, we checked the air shaft, we checked the main bedding and the yaw motor performance. We checked it on the toughest, on the harshest conditions, and its performance will go on. So I mentioned you about the offshore feature. We said that we designed it for offshore, and the turbines always get lightning. This is inevitable. 60% of the wind fields have the potential of lightning, so lightning protection is crucial. So we designed a Faraday cage. We designed fiberglass canopy laminated with wire mesh to offer Faraday cage protection, and we had fire protective paint. So what's the difference of this design? While Siemens designs, we designed it for standard transport limitations, which means that transporting and installing requires the equipment that whichever equipment is used for regular equipment. And as a result, we didn't need any specific transportation vehicle or a crane. And nacelle is transport in one piece to the field to minimize expensive and risky on-site assembly of critical components. This is a major adventure of our design. On the other hand, when we talk about maintenance, we removed the gearbox so that we could minimize the wearing parts, and we optimized our maintainability. And of course, Siemens is a leading brand on spare parts. And we also have a system that we can diagnose problems better. So as a result, with turbine magnets, with permanent magnets, we had increased efficiency, while we reduced the number of wearing parts, and we had a compact and lightweight design of the nacelles, so installation was also easier. So in terms of the investors, we give you enhanced performance, we give you easier maintenance, and about the transport and the installation, we don't need anything more than the standards. In terms of the costs, we see its reflections. We talked about the direct drive technology, but another important thing is its unique blade design. As you know, Siemens acquired bonus firm, and then we moved on. So our blade design and its cutting was unique to Siemens. And our blade design gives us the opportunity to increase lift and harvest maximum energy from the wind. There you can see the classical blades cutting, and you know the efficiency is low when the blade is closer to the hub, but as I said, we increased our efficiency with our unique cutting blades. So let's pick an example, direct drive 3.0113. This is also available in Turkey. Its class is 2A, 3 megawatts. We can see the design conditions. We can have 53% more capacity, and it is visible. This unit can give you the maximum performance at its peak, and this was in serial production in 2012, so this is not that new for us. So we improved and we designed, and as a result, when we compare, we see the power curve in our graphics. So wind speed is estimated as 7 meters per second. This is the average in Turkey. When we compare our own two models, we see an improvement of 38%, and on the annual energy production, again we take the average wind speed, we could improve ourselves by 17%. This is important, as Siemens, the R&D and the design and its changes gave us 17% of improvement, and this lowers the energy unit price. This is a huge benefit for us. So again, what I want to emphasize is permanent magnets enables us to reach higher performances. We have a simple design with less moving parts, and this reduces the complexity and the need for maintenance. Our design is compact and lightweight. For example, we have gearbox for 2.3 megawatts, and we have also permanent magnets for 3 megawatts. Their weight is the same. I mean, you can understand from this example. With our innovation, this machine can lift higher weights. So this gave us the opportunity to have wider bladings. Right now we are at the 113 meters of blading diameter. Of course, this will also benefit the investor as well. And from now on, I will be glad to answer any kind of your question. Thank you. Mr. Mahir Tosun, thank you so much. We learned a lot about the permanent magnets, about the compact components, and this was such a perfect presentation of Siemens. And now from Nordex Energy, Jan Hagen, the floor is yours.
Thank you for that. So mic is working. Excellent. Great, I'm very happy to be here. It's a pleasure, and I'm very amazed to see so much interest at this late hour of the day. Very impressed by a very vibrant convention here, and it's a pleasure to talk to you about our Nordex product development progress that we've made over the last year. And we'll jump right into this with this picture of our generation delta turbine that is in the field, and that is one of the core topics that I want to talk about. The fact that our latest technology is operating and producing power as we speak, just some months after we have announced them to the market. So let's hope that this works. I want to start out highlighting our evolutionary product strategy. So Nordex has been in the multi-megawatt segment since the year 2000. We have been shipping one of the first serially produced multi-megawatt turbines with N80 in the year 2000. Since then have developed step by step to generation beta, generation gamma, all of which are active in Turkey these days. And what I want to highlight is that the global availability of our fleet is 98.1% in the year 2012, based on close to 2,000 turbines operating under Nordex service, which is a great result of step-by-step introducing the learnings from the field into our technology that we're selling. So it's more than 13 years of experience. It's an installed base of more than 5 gigawatts out there. And the latest addition to this multi-megawatt platform of Nordex is our generation delta with the 2 turbines N100 3.3 and N117 3000. I will spend time now talking about 2 topics in particular: 117 2.4, the latest generation gamma turbine, and about generation delta afterwards. So let's look into this. N117 2.4, if you look at the wind speeds, wind classes, is our flagship light wind turbine these days. And I want to highlight 3 things about that turbine. First of all, it's the most efficient turbine for light wind sites with proven performance. All of the key performance characteristics of that turbine are confirmed by independent measurement institutes. So there's the power curve that comes in well with the warranted level. The noise emissions have been proven, as well as power quality. So the turbine is out there with proven performance and is giving us a lot of interest for light wind sites, also here in Turkey. I will come to that in a second. Then the second thing that's important about this turbine is the fact that it's fully certified. Nordex has achieved the type certificate for N117 2.4 within the last months, ahead of schedule. Very proud of that. So it's fully certified according to the international standards, in the sense that all the field measurements and validation exercises have been completed, an important milestone for our turbine. Then I've talked about significant interest in this turbine. If you look at that map, it's taking off worldwide. We have more than 300 turbines of N117 2.4 under contract, firmly in order intake today, and dozens of them out there in the field across the world. Wind farms operating in the US, in Finland, in Germany, and under construction currently on diverse sites as Uruguay, northern Finland again, and Ireland. In a wide variety of financing forms also that are behind those projects. So complex project finance deals behind that. And that's certainly an impressive track record, an impressive interest also in this turbine. And we're very keen to shortly talk about a small flag that you see there. Of course, in Turkey, there is a first wind farm that is using N117 2.4 that will be published shortly, that has been closed. for installation in the next year. So much about N117 2.4, and I want to spend the rest of my time talking about our generation Delta, which completes our product portfolio with 2 turbines for strong and medium wind conditions, N117 3 megawatt and N100 3.3. 2 turbines ideally suited for the Turkish market. The Turkish market is certainly among the key focus markets for these turbines. Some interesting projects for the strong wind turbine in 100 3.3, and a lot of interest also in 117 3 megawatt. And I will go into depth on those 2 turbines in the next couple of slides. Let's first look at the 2 turbines as such. Key features of interest for the Turkish market, I think, is that it's larger rotors. Something happened here. It's larger rotors, it's stronger power for the wind classes 1A and 2A, so for wind conditions that prevail on quite a number of those sites here in Turkey. That is a 100-meter rotor for class 1, up to a 100-meter tower. Certainly of importance also altitude of installation. Those turbines can operate at heights of sea level up to 2,000 meters, and noteworthy also the availability of a hot climate package for the class 2 N117 3 megawatt machine, which will certainly be of interest also for operation above 40 degrees Celsius. Now, if we look at that a bit more closely, Nordex is building on this evolutionary product strategy, which builds very much on proven technical concepts. Our generation Delta turbines share key technical concepts with the generation Gamma and earlier generations from this platform. Those being the electrical system, which is a proven and economical double-fed induction generator setup, which does not use permanent magnets purposefully, because we don't want to be exposed to volatility in the raw material markets. We believe, and we're delighted to see that a number of competitors return to TWEC setups, believing the same, that we will be able to meet future grid code compatibility with those electrical systems. The same is true for our drivetrain concept. We're sticking to modular drivetrain and our tried and tested gearbox setup. We're using proven wind gearboxes in this turbine platform. But what's most important really about those generation Delta turbines is the fact that we're using proven aerodynamic designs. Those rotor blades are tested blades and are measured blades that we have used in our generation Gamma turbines, also in Turkey. This comes with an important aspect. We can use those molds that we have deployed for those blades also for production of generation Delta blades. When you look at N117 2.4 and N117 3000, it's not by coincidence that I put the Turkish flag there, because those will be available from production in Turkey as of 2014, and will be thus eligible for the booster into the feed-in tariff, which is important to the economics of projects. Now, another thing that those generations share is the supply base. We're relying on the same set of suppliers with our turbines, and the first supplier set is virtually unchanged. So proven technology that we're using in those turbines, that we're taking to the next level of evolution, where we're working on 3 fields in particular. We're working on increased annual energy production, which is the outcome of larger rotors and larger nominal capacity. We have taken a select number of measures to increase reliability of these turbines, even further and to drive availabilities up. And we've improved the service and the health and safety friendliness of the turbines, purposefully to drive operating expenditure of the wind farms down. So all in all, we're working on 3 leverages to drive the cost of producing a kilowatt hour of electricity with those turbines down significantly, and that's what we're doing for strong and medium wind sites with those turbines. Now, here's an illustration of how this looks in terms of the power curve. We see our previous class 2 offering in N100 2.5 and the N117 3 megawatt in dark blue. and we see the effect of both the larger swept area, the larger rotor, as well as the stronger rated output in here. And this comes down to a whopping 22% increase in annual energy production at 8 meters built. Very common at 100 meter, also on Turkish projects. And that is if you use the lowest tower available. If you have a chance and the project benefits from a higher tower or can take higher towers, you have a chance to increase this up to 31%, the gain in annual energy production. So much about increasing annual energy production, significant gains at constant sound power levels within the wind class, notably. Then we have taken a select number of measures to improve the reliability of the turbines. We have introduced state-of-the-art control infrastructure, which is more robust and faster. So the nerval system of the turbine has been upgraded to an industrial Ethernet-based solution. We have introduced an advanced slip ring where data transmission to the hub of the turbine is now optical, which improves reliability of the communication with our pitch system. We've optimized the cooling system, as you will see in some of the next slides. Now, the other thing that is very close to our heart is health and safety and service economics. Those turbines come with protected hub access, so the path into the turbine is not longer at the open air, but it's protected, which is important to customers in climate zones that have a lot of frost and ice. In particular, and in health and safety concerned markets in particular also as well. The ergonomics inside the nacelle are very spacious and allow for fast and economic service. And in particular, we have designed the generation delta turbines for an annual service interval. So one planned visit to the turbine every year, which you can schedule in wind-poor parts of the year. And that has been done by select measures, as for example, automatic lubrication of the pitch-bearing raceways, which had to be introduced. So purposeful design for reduced necessity to go to the turbine in the plant manner. Then, when we launched those turbines in spring this year, we did that in Vienna, in Austria, and we did that here in Istanbul in spring when our general manager presented Generation Delta to the Turkish market. And at the time we made three promises, and one of them was that by June 2013 we would have the first turbines installed and would have obtained major certification. We would install up to 8 turbines in the year 2013, and we would start serial production in early 2014. And I'm happy to say that we're on track for all of those milestones, and that's what I will finish up with. We have obtained the design evaluation conformity statements for those turbines, so they're IEC certified, which is an important milestone. Furthermore, we have installed the first turbines, and I'm finishing off with some pictures. Here's the wind farm Janeby in northern Germany. 2 Generation Delta turbines operating these days and feeding in. They've been installed in summertime, as you can see, and we're feeding in for the first time right after. N100 3.3 on a 100 meter tower, and N117 3 megawatt on a 91 meter tower. Now there's some more impressions from this turbine in the field. It's been put into operation, as I said. Field testing and measurement is currently ongoing. And we had some real extreme testing in the field happening over the last weekend, where a heavy storm hit northern Germany that has been leaving a lot of damage to forests up there. Our turbines saw a gust of 49.4 meters per second in the 3-second average without incidents. Of course, it has not been producing at that wind speed, but it's safely returned into service. And around those stormy days, the highest yield in one day in a 24-hour cycle was more than 69 megawatt hours, which is probably as close as can get to perfect with a 3 megawatt turbine. So very good feedback from the field so far. Then here's the third turbine that's out there. That's up in Denmark. It's an N100 3.3 on a 75 meter tower, also with a met mast that is, I can assure you, not interfering with the rotor. That is just the perspective here. And furthermore, there's installations currently ongoing in Finland of 2 turbines in the first cold climate application. So a team of Nordex people working hard to take this, to commission this wind farm, and there are further projects in Germany that will be going into installation shortly. So we're on track when it comes to going into the field, and we're very delighted to say that we have also signed the first larger deals for Generation Delta, apart from the projects that you've seen. One that is very close to our heart is the Mevar project. It's a 24 turbine deal far north in Sweden. It's N173 megawatt. It will be producing in summer 2014. The foundations have been cast. And importantly for a new product, it's a notable owner and investor that's behind this. It's Allianz, an insurance. And we're very delighted to see them on board with this product at a very early stage, giving us the trust into this product alongside with O2, the project developer, and Google, who will be buying the power for 10 years for their data center in northern Finland. So this is the first commercial project, and I will close on summarizing that I hope to have given you some ideas to what extent our Generation Delta will drive cost of energy down for medium and strong wind sites. And last but not least, our Generation Delta will be completed with a Class 3 turbine, a larger rotor turbine for light wind applications. And it will be coming soon. We'll be announcing within the next couple of weeks. And I will leave you with this black screen, and I'm happy to take your questions. Thank you.
Thank you for your beautiful presentation and introducing the turbines. Now Turkey sales manager of Enercon will have the floor. Thank you, dear visitors. Good evening. This is the last session of today, and you're still here. You still have the patience to be listening to us. I'd like to introduce the investments of Enercon in Turkey. We know the Turkish outlook for Turkish wind energy. In terms of turbines, October figures of this year shows that we have finished almost 545 turbines. This means a share of 40%. It means that we installed 1 out of 2 turbines in Turkey. Some of them are small turbines. Here are some examples of our project fields. The installed capacity of our turbines is 750 megawatts. In the European market, as of 2012, we are the second, especially in Germany. We are very active. We have a market share of 60%. In the world market, the situation is a bit more different. We are ranking on the top ranks. but we are aiming for higher ranks. Enercon currently has an installed capacity of 31 gigawatts in the world, thanks to the direct drive system, which was introduced to Turkey for the first time by Enercon. The most important thing about Enercon turbines is the fact that almost 90% of the turbines are powered by Enercon. Are produced by Enercon. One of its advantages is the fact that we have our own R&D facilities. Our production facilities are spread across the world, including Turkey, Brazil, Sweden, Portugal, France and Austria. In total, we are present in 33 countries with a capacity of more than 50 megawatts. This is the example of our production facilities. Our manufacturing facilities in Turkey is among the first examples in this country. In 2002, there was no law on energy. Enercon entered the Turkish market by relying on its potential. It started its blade manufacturing in 2002. Our total area of activity is over 32,000 square meters. Currently, we are manufacturing blades for some turbines in this factory. Since 2009, we have a concrete tower factory. It is wholly owned by Enercon. Here we manufacture the concrete components of the towers. We have gained some key players of this market into the industry, including Çimtaş, which has started working with other manufacturers as well. Let's have a look at our product portfolio. We have turbines with a capacity of under 1 megawatt. These are E44, E48 and E53. These are three alternatives to three different types of winds. This is how we can also serve the markets which do not require license, because these are turbines with a power under 1 megawatt. E44 turbines are convenient for other kinds of manufacturing, our production sites. We also have turbines with a power of higher than 3 megawatts. These are some examples of products from our product portfolio. E126 has a huge diameter. We were talking about direct drive technology. Ours is electromagnetic direct drive. It has a permanent stator and a rotor inside. Here there is an alternate voltage in the generator. This voltage is filtered and then transmitted to the converters to be sent back to the filters again. This is how it connects to the grid in the end. Inside the turbine is a generator, rotor, and a stator. This is a permanent part. There is only 2 millimeters between the last two parts. The electricity generated is transmitted here, which sends it back to the tower again. In between the parts there is a transformator which converts it into the alternate voltage again before it connects to the grid. You can see it on the right hand side.
Orta gerilim ve alt gerilim şartları ve ortada transformatörün bulunduğu 3 katlı bir motor parçamız var. Ve burada tekrar alternatif akıma çevriliyor. Ve dediğimiz gibi 0.4 kW'dan 34.5'a kadar bağlanıp şebekeye bağlanıyoruz. Bunu tekrar şu şekilde gerçekten sahada görebiliriz.
Wind energy has always been an alternative energy, as you saw in other presentations. We tend to not just see it as an alternative energy, we'd like to consider it as a significant source of energy. We are carrying out R&D activities to this end. Even in the absence of any wind, we make the most of our technologies and operate the turbines in a way to be in full compliance with the applicable regulations. It's also a budget-friendly solution. We are also working on flywheel and other components. We are aiming to stock electricity for a period of time. That's why we are also carrying out some R&D activities. We have some offshore facilities which transmit electricity to some areas of the world which do not have a direct connection with the grid. And these kinds of islands that do not have a direct access to electricity receive electricity thanks to wind at a high rate. We are conducting 12 projects in this field. Here are the components which create the highest number of problems. This is a graph. This is the turbine still times. Please be aware that this long red column is a part that we don't have. We also use a component called blade adapter inside the hub. Blades are starting to be the components which are exposed to the highest amount of damages. We know turbine manufacturers suffering from that. The blade adapter means flexibility of blades, which helps us solving such problems. Thanks to hydraulic or mechanical brakes, especially thanks to direct drive technology. Turbines' life cycle is extended, especially in the case of projects with high capacities.
Hidrolikler vesaire gibi parçaların bize bulunmasından dolayı ve buradaki özellikle direct drive sistemindeki türbinlerin özel projelerde daha türbülanslı ve yüksek rüzgar hızı olan projelerde, yani yükün çok olduğu projelerde türbinlerin uzun ömürlü, daha çok çalışma saati olan türbinler olduğunda görmüş oluyoruz. Kanat dizaynına gelecek olursak,
I'd also like to talk about the blade design. Here is a general look. This is a general design of blades. Every manufacturer has their own specific design. We have a different nacelle which looks like an egg. That's why our blades fill in the gap between the blades themselves and the blade themselves and the hub. Only thanks to this difference in the design, we are achieving a 20% higher productivity. Enagon also pioneered a technology which is somehow can be described as blade squeezing technology. In Turkey, the rates of frost are quite high, especially at higher altitudes, including southern Marmara and internal Aegean region. When it's below -2 centigrades, it's really preparing the conditions for frost. When the weather drops down below -7 centigrades, the weather gets drier. That's why we don't see frost. Under the circumstances of frost, the blades have to carry an extra burden. There is also this danger that blades throw the frost, the fragments of ice when they continue operating. These are risks posed against injuries. In such circumstances, turbines stop themselves and wait until the frost defragments again. As Enagon, we first tried to use a fan system which blew warm air to the blades in order to melt the ice. And seeing that it was a smart idea, we have been using that technology in Turkey as well. The performance level was 15 or 20% in our experimental R&D facilities in Sweden and Czech Republic. The level of productivity thanks to these heaters is almost 30% in Turkey. One other prominent feature of our direct drive technology is that turbines do not automatically close down. In general, turbines shut down themselves in order to protect themselves at high wind speeds, waiting for the wind to reduce its speed for a period of 10 minutes. Then they open themselves again, activate themselves again automatically. This average period of 10 minutes can be a couple of hours, sometimes a couple of days. However, as the turbines shut themselves down, they always get to be disconnected from the grid in order to avoid losses. Direct drive technology has helped us again. Here is an illustration from the SCADA system showing that turbines are still operational at high speeds of wind. Turbines continue their operation at high speeds of wind, and when the wind slows down, the blades open up to the full extent and still continue their operation. In addition to steel towers, we pioneered another technology, which is hybrid towers. As we are the pioneers, we are quite experienced in this field. Here are the rates of our concrete and steel towers. Hybrid towers offer some advantages both in terms of transportation and assembly. That's why we are quite proud of this system. The heights of concrete towers start from 83 meters. The highest tower is 149 meters. It is actually 150 meters with the addition of the hub, or 153 meters. This is our highest tower. We believe that using higher towers in some productive sites is a better idea, especially in terms of catching the wind and higher speed wind. But we don't always need it, thanks to the geographical structure of Turkey. The hubs of concrete towers and the bridges of concrete towers are manufactured in 3 segments, and they are assembled together at the site. In the past, we used to benefit from resin and other sticking adhesive materials in between these segments, but it had a disadvantage. It reduced the speed of the erection of these towers, and we were unable to work under some certain temperatures. Thanks to this system, now we don't need an additional reinforcement material. Only with a stretching operation, each segment is connected to each other under any condition. All our turbines feature direct drive system, and their power is over 21,000 megawatts. Since 1991, Enercon has been manufacturing direct drive system. Before 1991, we used to employ normal gearbox systems, but in this field, in direct drive field, we have the highest number of references. Can we wrap it up? Okay, I'm going to be faster. I'm trying to be faster. Our special types of turbines will help us achieve a higher rate of efficiency. We are waiting for necessary approvals to put them in the market in Turkey. E92 doesn't only mean an extension of the blade, but it also means the optimization of aerodynamics of the blades. It eases the burden, and it almost has the same weight as our E82 turbines. We have been an environmentally sensitive company, especially in terms of noise. We have a system. Wild birds need to be really silent when they are hunting, and that's why behind their wings is a erect part. This is what we are also applying on the ends of our blades. By this we really decrease the level of noise significantly, especially in sites close to residential areas. E115 turbine is transported thanks to very sophisticated solutions the world of logistics offers. This turbine has a specific R&D development. We are using a rolling system here. The blades consists of 2 parts or 4 parts. The front part that connects with the hub has a rolling system, and the other part is sticked with normal conventional methods like resin. The reason as to why we separated these 2 parts is any possible absence of methods that prevent us from transporting it. So in such conditions we are still able to carry it in 2 parts. We are quite ambitious in terms of service, which has a broad coverage, and now we are working on an agreement in a way to offer all the spare parts. In Turkey, the term of our agreements is 15 years. In Germany, this term is 20 years. Our aim is to extend it to 20 years in Turkey. Let's have a look at EMRA analysis of availability. Can I hear your last words, please? Okay, Mr. Chair is asking me to stop. That's why I'm ending my words. Thank you very much for listening. I'd be happy to answer any of your questions. Many thanks to Arif Bey for his presentation. Now the word belongs to the other panelist.
Good afternoon. Thank you, Mr. Chairman, for inviting me in this presentation about new technology. I am speaking about special new technology because it is not about wind turbines, but it is about wind computation. So the question is to present computational fluid dynamics like new technology in the estimation of the wind and all the characteristics of the wind. Okay, just a few words about Methodyne. So Methodyne has been created 10 years ago, and is proposing some software for computing the wind. The most famous is Methodyne WT, and Methodyne WT is a software which computes the wind in complex terrain. So we will see why it is adapted to complex terrain. And also, of course, the production of electricity and all the characteristics of the wind that can affect the life duration of the wind turbines. Also, we have a software called Global Wind, which can compute the wind inside cities. In particular, it can be applied to small wind. And also, we work on forecast, so we have a software for that. And similar wind, it is to simulate the wind at very little scale for building applications. Yes. Yes. Methodin is a company which sells software everywhere in the world, and especially we have an affiliate company in China, in India, and in America, and we have a distributor in Turkey, which is a usual company. I will speak about getting benefits from CFD for 4 topics. Wind resource assessment, which is well known, but also which is less used, analysis of wind parks performance and optimization, collection of LiDAR measurements in complex terrain, and downscaling for production forecast. The object of CFD solver is to solve the full Navier-Stokes equations, which are the equations of fluid mechanics, very classical. So without making any hypothesis of little perturbations, like it is done, for instance, in the linear model like WASP. That is the reason why it can be applied in any kind of terrain. It is fluid mechanics, but it is also meteorology. So what is different from software like Fluent or CFX and so on, it is that we have to take account of the particularities of the atmosphere. For instance, for the turbulence modeling, for the ground conditions, and here you have some equations, for instance, for the ground conditions in case of canopy. Canopy is a forest, for instance, or cities, or without canopy. So today I will not enter into the details, of course. So this kind of software has to be validated in order that people can believe, of course, what they obtain. So different kinds of validation. First, we have to validate on very simple case to be sure that the roughness effects, for instance, are well reproduced by the code. And generally, it's compared to typical theory, which generally are semi-empirical theory because they use the data in the atmosphere. Here you see a comparison between result from Meteodyne, the blue line, and the points which are under the blue line for the theory of Manilobukov. For a case of roughness 1 meter. 1 meter roughness is about a forest with trees of about 20 to 30 meters height. We compare, of course, the wind velocity and the turbulence intensity. So comparison on a very simple case, but it is necessary, of course. Another simple case, it is the evolution of the boundary layer when you have a change of roughness. For instance, when the wind comes from the sea to go inland, and then you have a height of an internal boundary layer. The internal boundary layer is the boundary layer where you see the effect of the new roughness. And you see here a graph where we compare the line is a computation, so the height of the roughness as a function of the distance to the change of roughness, what we call the fetch, and compare with different experiments, and we see that we are inside the experiment. Another effect that we have to validate is the effect of stability. Thermal stability can be an important factor for the extrapolation of the wind, so we have to take it into account. And here you see a comparison on a flat terrain between different theoretical curves that you can find in the literature for different stability cases, and comparison with computations for mean wind speed on the left and turbulence intensity on the right. So now we have also to consider real cases. So one of the most famous one is the Ascov-Ventez case. WASP has been calibrated on this case in particular. It is a very interesting case because we have a lot of measurements. So you see on the left a line of anemometers. Maybe about 50 anemometers were installed at 10 meters height, and then we can compare on different lines. You have the line AA on the right at the top. The measurements are the red squares, and the computation for different configuration are the lines. So you see the maximum wind speed, for instance, at the top of the hill is about 90% more than upstream. So the model can very well produce that effect. Okay, so I show here only a little part of the validation of this case. There are a lot of things. Another case which is interesting because it is a very, very complex terrain. It is located in India. It is Andhra Lake Wind Park, and it has been commissioned by MLP in Mumbai. So you see here so the very sharp slopes that we can observe. And what is interesting is that in this case we have a 5 measurement mast. Wind speed was measured every 10 minutes during 7 years for some of the mast, and at least 1 year in common for all the masts. So it's an ideal case to validate CLD codes. You see here 5 masts. And you see how the orography is very sharp and very complicated. And you can observe also forests on the slopes. So the computations were made with Meteodyne WT. So it's a very special case because both the domain is very large. The wind farm is 30 kilometers by 30 kilometers area, and we have to have a very fine resolution because the orography is very sharp. So the horizontal resolution is 20 meters, vertical 40 meters, so it leads to a case of 60 million cells. For people who know CLD, they know that it's a very rare case. So we have done it with computer, which need at least 60 megaoctet RAM. And the computational time is only 8 hours for one direction, and we have considered 36 directions with 8 processors. So the total computation time was only 72 hours. So it is very operational even for such a case. You see here for two directions. On the left, the wind speed for west wind, and on the right, also wind speed coefficient for the eastern wind. And you see where the masts are located on the site. This is turbulence intensity. And then we make the validation by comparing the mast, one compared with the others. And here you see on the graph the comparison between measured mean wind speed over 1 year period and calculated mean wind speed, started from one mast. So we see that the nominal standard error is about 5%. It is generally what we say for CFD. So for such a complex terrain, 5% we were very, very satisfied. So 5% on the mean wind speed. So on the production, of course, we have made simulation. Changing the wind speed of 5% in this case change the energy output of about 12%. So we say that it is not possible to get much better accuracy for such a complex site. But I think it is enough if we take it into account. You know that when you make an evaluation of production on a wind park, you have to evaluate P50, P75, P90, the probability of exceeding a certain value, and so it is taken into account in these estimations. Another case which is interesting because it is a blind test which has been launched by the European Wind Energy Association. It is a wind park in Scotland, and we had input data measurements, and we had to estimate the production of the wind park. And I think at least 30 teams in Europe and in the world have answered to this exercise. We have not the detail of each team, of course, but each team has its own results. So I will give you the results of Meteodyne. This is the site, not very complex, but you see there are hills and forests. 5 million points were enough for such a case. This is a view of the mean wind speed that we have computed on the site for one direction, which is prevailing wind direction. And then the statistics of wind speed were given at one mast, and we had to estimate the production of each wind turbine. And in this case, the wind park is commissioned, so we know exactly how much it produces. So it's an interesting case. And I repeat it was a blind test. It means that we didn't know anything about the results. So on the graph above, you see the 22 wind turbines, T1, T2, T3, and the mean wind speed at each of the wind turbines. So you see that the mean wind speed goes from 7.5 to 8.5 meters per second. And you see the result by Meteodyne on the mean wind speed and on the turbulence intensity. And now the comparison with observations. The only observation is the production of each wind turbine. So you see it in the green line, and the value given by Meteodyne in red. So I must recognize that we are a little bit lucky because the observation was 76.4 and we obtained the sum of all the wind turbine 76.2. So that we don't pretend to be at 1% or 2% accuracy. So, but it is a result. If we compare now each wind turbine separately, we see that the maximum error was 200 megawatts Earth. So it means that the maximum error for one wind turbine is 7%, and for the root mean square error over all the wind turbines is about 3%.
Mr. Didier, can we have the final words, please?
Yes. So another case, it is a wind atlas in the southeast of France. We have measurements in red and the computations in the blue stations. And so we compare measurements at the blue station with computed values at the same stations. So we see also that in this case the error is 5%. So I'm afraid I will not have to tell too much now about performance of CFD, but I just recall other applications that are possible. Analysis of wind park performances, so estimation of the wind curves, of course, because we need to know the wind speed at each wind turbine. So the only way to have it is to compute it. We observe also that we can compute turbulence intensity, vertical inclination of the wind at each wind turbine, and very often, it is a case in Germany, it is a very good way to know why a wind turbine produces more than another one, even if the mean wind speed is the same. We see that there are big differences, and CFD can help you to analyze these problems. Of course, measurement leaders, probably you know, have to be corrected. So CFD gives you the correction coefficients, and we have sometimes error of 5 to 10% on the measurements that can be corrected. And also CFD is used for forecast because mesoscale model do not give the result at each wind turbine. You are obliged to use CFD to know exactly the wind at each wind turbine and to estimate specific effects. And in particular, you can consider wakes. If the wind turbine is out of order or not, you consider the wake or not. So my conclusion is that, okay, CFD is a new technology that has been validated, which is used now very commonly for wind resource assessment, particularly in complex terrain. But we must not forget that CFD can be used for most of other applications, like, of course, LiDAR corrections, like optimization and analysis of problems in wind farms, like downscaling for forecast, and probably I forget other applications. Thank you for your attention.
Many thanks to you for this sophisticated communication. Now I'm giving the floor to the other panelists.
The floor is yours.
Yes, good evening also from my side. My name is Markus Altenschulte. I'm coming from General Electric, and I want to tell you a little bit about what we are thinking for the TWEC, what we can do. And I promise I will keep it short because I think I'm the last speaker and I don't want to keep you from your home. So just give me a few minutes, a few slides, but I promise it will be short. So when you look at this picture, it shows how the energy, the world, the electricity looks today.
And I thought it's an interesting one because what do we think we expect in the next 20 years? In the past days or today, there's a lot of questions about Turkey adding 20 gigawatt to the electrical grid and energy demand. And I was thinking that if you look now carefully to the next slide, you maybe understand why we are concerned and why we're here in Turkey with our products. If you see this picture, and I switched a few times, so please look for Turkey, you see that we expect, and this is not only GE, I think this is everybody here, that there is a good reason that we need more electricity, that we need more power, that wind will be part of that. So I think it's cut it out a little bit, or no, not on this one. So the reason I'm here is because General Electric is producing equipment to generate electricity. And we can say that about 25% of the daily electricity in the world is produced by different type of equipment from GE. And the wind turbine is one piece where I mostly care about. And when we think about what we can do for the future and how this is impacting us in the grid, we are trying to look forward and we try to look around the corner. So what we announce here today maybe is our new product for Turkey. I had the big benefit to be on the ICCI conference here earlier this year, and one of the questions of the customers in the audience was, why does GE not give us a 3.x megawatt turbine? The answer is, we listen to you, this is our result. So today we are offering for the Turkish customers and for others in Europe a new turbine based on a 2.5 megawatt baseline, which has 12% more output power, so from 285 to 3.2 megawatt rated output power, and this gives you about 5% more annual energy production. The turbine is based on our fleet of over 1,200 turbines of only 2.5. GE globally has more than 22,000 already. And new is that we use the combination here of the existing 285, which we see in Turkey already, plus the new 2.5 120 low wind turbine introduced earlier this year. And one big piece we take over also for the 3.2 is the brilliant turbine, and specifically the opportunity to hook up to the turbine and battery or energy storage system. Now, why is this important? Because if you add more wind power to the grid, we need to think about how do we ensure that the grid stays stable. Wind turbines that are getting to the grid need to support the grid operators. GE always had very, innovative products here. So the wind control, making sure that the wind farm is like a power plant control. Wind right through, make sure that in error situations, the turbine stays on the grid. Today we can survive 500 milliseconds without grid voltage. That's an incredible product. We have wind free. Many years ago I was saying, I can give you reactive power even if the wind is not blowing. So the next innovation is, I want to give you active power if the wind is not blowing. And obviously with an energy storage, we give you that. So energy storage can give you active power, either if the turbine is running and it's slowing down a little bit, or even if the wind is not blowing, I can use the battery storage to feed a little bit active power to the grid, which is important. And I come to the next page to the reason why we think it's important. And also wind inertia, which is helping there. So wind inertia comes into the same place. All of this should be integrated, so to make it very easy understandable, the battery system will be connected to the power system, the power converter and transformer of each turbine. The benefit is that each turbine has a small battery, and you don't need a central station where you need a transformer system, where you need a power converter, a control system. All of that is managed as part of the turbine equipment. And it's an option that also can be added later as a retrofit. So if a customer after a few years find out it's an option they can make money on, and where the grid is happy to support that, there we can play. Here are the three easy cases why we think that it matters to have in the future something like a better grid support. On the top, you see the so-called ramp rate control. In the moment the grid is asking you, when the wind is picking up, you cannot so quickly use more power. You need to control how much per second per minute you can add. But even if you do that, sometimes the wind is going up and down at that time. That's the nature of the wind. Our energy storage can take exceeded power. Instead of spilling it or wasting it, we can pump this to store it in the battery system. And if the wind is a little bit too low in this moment, we can bring back the active power out of the battery through the converter to the grid. So we subsidize each other. The second chart shows predictable power. If you have to go to your grid operator and tell him, tomorrow I will give you, today I will give you 20 megawatt power. You use systems like we just learned, wind forecasting. But each forecast has some error margin. And sometimes you need to pay for the missing energy. If you have this kind of situation, energy storage can keep this, missing gap and close it. So if you have about 5 to 8% rated of the power in the battery, it doesn't matter if you have an error forecast of 5% for the next hour. So energy storage can help you predict a stable power. You see it here in the red line and the green line. The red line is the power which you would produce if you just follow the wind. The green power is what is the stable power after you're committed to a certain level and we're balancing around that. So it's a very small gap around it. And the last point, which is really more faced towards the stability of the grid in the future, more and more wind comes through. So somebody somehow needs to make sure that even if the frequency drops, so if there's more energy demand than in the moment can be produced, that at least for a short moment in the first 2 minutes, in the first 10 minutes, somebody has to give power to the people, or somebody has to switch off the people who try to take it. With the frequency regulation system, it's easy to, disrate the power. We call it normally energy containment. That's easy. Too much frequency, you just cut down a little bit the wind turbines. But if the turbines need to produce more power and the wind is not there, this is where we believe that then a battery can jump in and help the grid to stay stable in this short moment. So these are more or less the point. If you look on the chart now, the experience we use here is really based on our 2.5 fleet. You see a little bit in the moment we are, by end of November, the latest number I got, we have over 1,300 turbines on the grid already of this family. The 3.2 is part of the 2.5 megawatt family because we're sharing the same components. It's not a new machine design or something. It's not a different weight. It's not a different size of blade. You can transport it like a 285 or even as a 2.5 100. So we stay in the same boundary limits. And the advantage we see is that we're staying in this existing fleet evolution experience. We are not going a step backwards in the reliability of the product. So the key message I want to give you today is that GE now listened to what the Turkish customers told us. We need a more powerful turbine. And with the 3.2103, I hope we have given you now a turbine that is making you happy about the more rated power. And if you have technical questions or other questions I don't touch today, please see us in our booth today or tomorrow. We are very happy to answer all your questions about what is behind our technology. So thank you very much.
Çok teşekkür ederiz. Sayın konuşmacıları.
Do you have any questions?
Alabiliriz.
Otherwise, I'm gonna end the panel. I guess there is no question. Thank you very much for your attention. Have a good evening and see you tomorrow.